Okay, so there's one last thing in this section that is useful. So we basically got that theorem that told us about how the determinant changes when you do elementary row operations to it, right? If you switch two rows, then you get the determinant becomes negative, right? Negative the original determinant. If you multiply a row, then you multiply the determinant by that alpha, right? If you add a multiple of a row onto another, then nothing happens. Okay. This is useful in so application is in the calculation of determinants. So you get the simplification, simplifying the calculation of determinants. And this is something that we basically kind of mentioned before. Right? Somebody gives you a matrix. Let's say it's 5, -2, 1, 3, 2, 0, 1, 1, 1. And it says calculate the determinant. So you could do your expansion by minors, or you could use the theorem that we just got. And you say, okay, well, what I'm going to do is do Gaussian reduction on this thing, and I'll keep track of how the determinant changes as I do my Gaussian reduction. Okay, right. So, and why do I like to do Gaussian reduction? Because at the end of it, I have a diagonal matrix. I have a triangular matrix, and the determinant of a triangular matrix is easy. I just need to multiply down the diagonal, right? So as long as I keep track of how things changed, I'll be able to figure out my original determinant easily. So I say, okay, I'm going to do Gaussian reduction on this thing. First thing I'm going to do is switch rows 1 and 3. Right? Row 1, switch with row 3. That gives me negative, right? The determinant becomes negative of what it was. So I get 1, 1, 1, 3, 2, 0, 5, -2, 1. Right? Okay. And then, I'm going to use this pivot to clear out the rows beneath, right? So I say, okay, I'm going to take row 2 and turn it into row 2 minus 3 of row 1. And that's not going to change, right? That doesn't change the determinant, so I don't introduce any other factor here. Okay, so I get 1, 1, 1. I get 0 minus 3, that becomes -1, minus 3 of that becomes -3, and 5, -2, 1. Okay. Because adding a multiple of one row onto another doesn't change the determinant. And you keep on going. And I know, I guess we'll do it, but it's not the most exciting thing. It's okay. So now I'm going to do the same thing to row 3. Row 3 becomes row 3 minus 5 of row 1, 1, 1, 1, 0, -1, -3, 0, minus 5 of that becomes -7, minus 5 of that becomes -4. And then you say, okay, maybe I'm going to pull out a -1 out of here, right? So I get -1 squared. Well, that's just +1, right? So 0, 1, 3. And 0, 7, -4. And now I'm going to take 7 of these guys and add them onto this. That doesn't change the determinant, so nothing happens. 1, 1, 1, 0, 1, 3, 0, 0, 21, 17. Right? So I'm done with my Gaussian reduction. And I say, I've got an upper triangular matrix. The determinant is easy to calculate, right? And so I see that my original matrix's determinant is 17. Okay. So instead of doing like expansion by minors and stuff, you can use the elementary row operations to reduce the matrix to row echelon form, keeping track of how you've altered the determinant along the way, and then at the end you end up with some factors here times something that's easy to calculate, just the product of the diagonals down the diagonals. Okay. So that's the application of that, and this is actually a true application in the sense that if you have a big matrix, it's very difficult actually it's computationally expensive to calculate the determinant, but it's a lot cheaper to do the Gaussian reduction first and then multiply down the diagonal. Okay, so now we enter chapter 3. So chapter 3 you can think of as the beginning of actual linear algebra. So what we were doing up until now, actually non-linear algebra. Now we're actually going to start doing some linear algebra. Okay. So chapter 3, fundamental concepts. And the point is this, that you have these vector spaces, right? We have these things called vector spaces, and you can do things with vectors. But in fact, there are a lot of things that behave like vectors, and so we consider those things to be vector spaces as well. Okay, so you already have some notion of what a vector space is. I'm sorry, you have some notion of what vectors are. Okay, like you've got this Euclidean space, you've got vectors, you can add them, you can multiply them by numbers, right? There's a zero vector, all these things. But it turns out that there are many things which have that same underlying structure. Okay, and so the idea of what is a vector is actually more general than you might have imagined. Okay, lots of things are basically vectors. Okay, lots of things are basically vectors. So I think the way to think about this is actually the parable of the cave, right? Plato's parable of the cave, right? Where he says that, there's you have all these shadows, but then in reality there's this thing that's casting the shadow, right? And the shadows may look different, but there's this one thing that underlies it. Okay, and this is the same thing, right? We have all these different things that behave like vectors, You want to think that there's this underlying ideal idea, like this underlying thing called vectors, right? And these are all just sort of instances of vectors. Okay, so what we're going to do today is basically extract that underlying thing and start thinking about that. Okay, so we're going to look at the abstract notion of a vector and vector space. Okay, and so this is why linear algebra is such a powerful thing, because you can actually apply it in many circumstances. Okay. So 3.1 is on vector spaces. Okay. So these are things that basically behave like your old Euclidean vectors, right? Vectors in Rn. Okay. So here we go. It's kind of a tedious definition. So let V be a set. Okay. You have a set of things. Okay. And that set of things has an addition on it. And a scale and multiplication. Okay. And what we mean by that is that given any pair of elements in our space, there exists a well-defined x plus y that's still in V, and given any element in the space and some number in R, there exists again a well-defined something called alpha x in V. Okay. So there's a way of creating a sum. Given any two guys, there's a way of creating a sum. Given any one guy and a number, there's a way of creating a scaling of that guy. So you have some space, and this space has some notion of addition and some notion of scalar multiplication. If blah 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 blah, then we say V is a vector space. And call its elements vectors. So, and this blah 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 is basically things that the addition and the scalar multiplication ought to satisfy. Okay. So here they are. If addition is commutative, if addition is associative, if there exists an element called 0 such that x plus 0 equals x for all x in V. Right? So there's a additive, what's called an additive identity. Additive identity. Right? There's a 0 element in there. If for all x there exists some sort of negative x such that x plus negative x is the 0 element, right? So there exists additive inverses. If alpha times a sum, the scaling of a sum is the sum of the scalings for all alpha in R, x, y, in V. If alpha plus beta, x equals alpha x plus beta x. If alpha beta x equals alpha times beta x, and 1 times x equals x all x, then we say V is a vector space. Yes.
So do all these things have to be true, or can only one of them be true?
No. If all these things are true, right? So if you have a set with an addition and a scalar multiplication and blah, 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 blah are all true, then we say the thing is a vector space.
Why do we need so restrictions?
That's just that's sort of what you would want a vector space to be, right? If you think about what you can do with your vectors, right? Think about your old vectors, right, in Rn. What can you do with them? Well, it doesn't matter how you add them, right? If you take two vectors, you can add them in opposite orders, right? You can add two guys and then a third, or you can add the last two add the first onto the last, some of the last two. Right? All these things are things that hold in your normal, in your old vectors. And so these are the things we're going to extract as the essence of what it means to be a vector space. So these things, these guys all here, all these things, they're called the vector space axioms. Vector space axioms. Okay, a couple of comments. One, this term scalar really means really should be element of a field. So it could be R, it could be the complex numbers. So really, when one talks about vector spaces, you say vector space, like a complex vector space, or a real vector space, or whatever. Where the scalars are allowed to be in the complex numbers, or the real numbers, or some other thing called a field. Okay. Remark number 2. The property that if x and y are in V, then x plus y is in V is called closed under addition. Closed under addition. Okay, so whenever you have two guys in the space and you add them, you stay within the space. You don't leave the space, you're closed under addition. Number 3, this 0 guy is actually unique. We didn't say it, but in fact, this 0 guy turns out to be unique. And the argument is one that we've seen before, I think, or seen something close to it before. I think we've seen it before. If both 0 and 0 prime are additive identities, then what you see is that 0 plus 0 prime is 0 prime, and 0 plus 0 prime is also 0. So they'd have to be the same guy. Everybody okay with this quick, very short argument here? If you had two guys that were both additive identities, well then, look at their sum. Since 0 is an additive identity, it plus 0 prime must be 0 prime. Since 0 prime is an additive identity, then it plus 0 must be 0. But that tells you that 0 and 0 prime are the same guy.
What do you mean by additive identity?
Additive identity. So something with the property that when you add it to somebody, nothing happens.
Okay.
Okay. So if we have two guys who both claim to be additive identities, then they both should have the property that when you add it to somebody, nothing happens, right? Well, if that's true of both of these guys, that forces them to be the same guy.
Why you add the 0
I want to show that 0 and 0 prime are the same. Right? I'm trying to show that there's only one additive identity. The thing is that if there are two, then if you consider their sum, you see that implies that they are the same, they're equal to each other. I'm trying to show that in this thing called a vector space, there's only one 0. Okay. there's only one zero vector. Okay, so you might be saying, of course, there's only one zero vector, right? There's only one zero vector because you're thinking about the Euclidean space, right? Okay, but we're not in Euclidean space anymore, right? We're not in Euclidean space anymore. We're in the world of abstract vector space. Okay, and in the world of abstract vector space, the only thing you know is these facts. Okay, and it turns out that in the world of abstract vector spaces, there is only one zero. There is only one zero vector, but it's a consequence of the third axiom. Yes.
Since it's an abstract vector space, does that mean it's almost impossible, or it is impossible to like have a geometric interpretation of a zero vector?
In some sense, yes. In some sense, yes. Right. So you're basically losing all geometry once you enter this world. Right. Because where's the geometry? Right. It's just right now all you have is a set, an addition, and a scalar multiplication, and a bunch of properties. That's it. Right? So it's just an idea now, right?
Or like to think about it like a zero vector, for example. Like, is there like a geometric interpretation of that, or is
It's
it
just
like
it is that which, when you add it to something, it's nothing. That thing doesn't change. That's it.
So
Yeah. Yes.
what is the key difference between a vector space and a Euclidean space?
Euclidean vector space is Rn. Okay, you've got your Rn, you've got your vectors, x1 through xn. Right? You can add them together. There are numbers involved, right? Like 1, 2, 3 plus 4, 5, 6, right? It's going to be equal to 5, 7, 9, right? You've got these numbers. You've got there's you can do. It's basically based on addition, right? This thing, there's no numbers. There's no numbers. There are no numbers yet. I mean, there are no numbers, period, except for the scaling numbers, right? You've got these things, and you're allowed to scale them. Okay, you can add them together, but when you add them together, it doesn't involve addition. It's just you add them together somehow. Yeah.
Also, kind of back to number 3, I
Yes.
guess.
Yeah.
So I see the second part where you have the zero vector plus the zero prime vector equals a zero prime vector. That
Mhm.
comes straight from A3.
Yeah.
But the first part,
Same thing. So if this guy is also an additive identity, then it has this property. Right?
so you're saying,
If you have two guys that satisfy, they both say, I'm the zero element.
okay.
If they both say, I'm the zero element, they actually turn out to be the same guy. Right? If they both say, I have the property that when I'm added onto somebody, that guy doesn't change, then it turns out that they're equal.
Okay.
Okay. So it's like, suppose they're two guys and they both say, I have the property that when you add me onto somebody, that I don't contribute anything. Okay.
So for A3, you could have written like that and zero prime vector. You could pretty much write a prime on any 0, 2, and it holds.
Yeah. Yeah.
Okay.
So suppose that 0 does this and 0 prime also
Okay.
does this.
Okay.
Okay. Then they must be the same guy. Everyone all right? Okay. Yeah. So my first class when I went to college was so-called finite dimensional vector spaces, which was basically like it started off with the definition of a field, and then went on to talk about vector spaces, but there were no numbers. It was just all abstract vector spaces, and I found it very, very sort of bizarre and hard to get my head around. You basically have to sort of think of these things as creatures, right? Or like they're constructs. They're sort of abstract constructs, and you think of them. Each of them has special properties, and they interact with each other in certain ways, right? But there's no, you don't think of them as, secretly you could think, okay, I don't want to think about these guys. I just want to think about the vectors underneath them. But it's actually to your advantage to sort of toss out the notion of vectors entirely, toss out the notion of Euclidean vectors entirely, and just think, okay, I've got these things. Right? I've got these things. They behave like this, and this is basically all of pure math. Right? You've got these things, and they behave in certain ways. Okay, so sort of like a biology of abstract constructs. Okay, okay. So, okay. But to make this a little bit more concrete, let me give you some examples of things that are vector spaces. Okay, I said that there are a lot of things that are vector spaces. Okay, here are some examples. Okay. Okay. So first example, dumb example, Euclidean space, right? Certainly, there's a way to add guys. There's a way of multiplying by numbers. Addition is commutative, associative. There's a zero vector, right? Namely, the guy 0, 0, 0, 0, 0. There's additive inverses, right? What's an additive inverse? If I have a vector, right, x1 to xn, then what's its additive inverse? Well, its additive inverse will be negative x1 to negative x1, right? Because when I add those guys together, I get the zero vector, right? And so on and so forth, right? You can multiply, blah, blah, blah. Okay, so this is an example, of course. Okay. Second example. Matrices. The set of n by n matrices, right? You can add two matrices together. You can multiply them by scalars, right? It doesn't matter what order you add them. Addition is commutative, associative. There's a zero matrix, right? What's a zero matrix? Well, it's the m by n matrix of all zeros, right? There's a matrix negative A. What's the matrix negative A? Well, it's just -1 times the A matrix, right? Right? You take your matrix and then you put -1 on every single element, and that's the additive inverse, right? So you have this wonderful equality here. Negative A is -1 times A, which seems very dumb, but it's actually saying something. The additive inverse is the scaling of the original by -1. The additive inverse is the scaling of the original guy by -1. Okay, so there's actually a statement involved, and so on and so forth. The space of all matrices, the space of m by n matrices is a vector space. Number 3, continuous functions. Continuous functions, say on AB. Okay, so this is denoted capital C AB. The set of continuous functions on AB. Okay, if you have two functions, you can add them together, right? Right? If I have two functions, f and g, I can add them together, right? The new function is given by this, it will give you the sum of the old functions, right? So I create a new function, right? Here it is, the sum guy, right? There's also a way of multiplying, right? If I'm talking about 5f, well, that's just the function that gives me back 5 times what f would have given me back, right? So you can take functions and you can add them together. You can take functions and you can scale them, right? It doesn't matter what order you add them. So addition is commutative, addition is associative, right? What's the zero vector? What function, when I add it on, doesn't do anything?
f of x equals 0.
F of x equals 0, right? So you just say this function, f of x equals 0 for all x. That's your zero vector, right? That's your zero vector, right? Because when you add that guy on, nothing happens, right? What's the additive inverse of a function? Right? If I have a function, right, then the additive inverse guy, well, you can guess, of course. It's just going to be -1 times f of x, right? Right? the guy that gives you back negative f of x. Right? Because if you add that guy onto your original guy, you get the 0 function. Right? You get the 0 vector. Okay. And you see that all the axioms hold, and so the set of continuous functions. Oh, there's something that we have to check. Closed under addition. If you take two continuous functions on AB and you add them together, do you still get a continuous function on AB? Yeah, you do. Right? You have two continuous functions, you add them together, it's still going to be a continuous function. Okay, so we are closed under addition, and if we scale, we're still going to be continuous, so we're okay. Right? We stay within the space. So, but those are things that we do have to check.
So the space is being continuous.
The space is the set of all continuous functions whose domain is AB. Okay, and you see that if you add two guys, you're still within that space, right? You can't add two continuous functions and get a discontinuous function, right? Okay, but if I said, is the space of discontinuous functions a vector space? The answer is no, and the reason is that you can add two discontinuous functions together and get a continuous function, right? If you think about it, you can, right? If I have one function that has a hole here, and then I have another function which has value 0 everywhere except at that hole, right? I add them together, I get a continuous function. So that space is not a vector space because it's not closed under addition, right? Because you can take two guys in your space and add them together, and you get something that's not in your space anymore. So not a vector space. Right? You could have one guy that looks like this. You could have one guy that looks like this. Right? And you add them together, and you get a continuous function. But you could say the space of all functions, period, would be a vector space. What about the space of differentiable functions? Is that a vector space? Yes.
Yeah.
Yes. Yeah. If you add two differentiable functions, it's still going to be differentiable. Okay. Last example. Number 4. P sub n. This is the notation that the book uses, and it uses it lots. So keep this one in mind. P sub n is the polynomials of degree less than n. Okay, so not less than or equal to n, but less than n. So P3 is quadratic polynomials, quadratic and lower polynomials. Okay. So this also turns out to be a vector space, right? Because you can add two polynomials together, and when you do, you don't increase the degree. You can multiply them by scalar, you still get a polynomial, and so on and so forth. So it's easy to check. So I hope you're starting to see that there's all these things that are actually like vectors, but they're not Euclidean space. Okay. Everyone's trying to enter the world or leave the world behind. So basically, we're entering the world of abstraction. Right? We're sort of like abstracting the notion and seeing the essence. Okay. So there are a bunch of other properties of vector spaces that we don't put in the axioms, and the reason is that they're consequences of the axioms. So there are things that you think, well, shouldn't this be true and shouldn't this be true? So there are other properties that you would sort of want to have in vector spaces, but in fact, they already are in there. We just didn't notice them yet. Okay. We just didn't remark on them yet. Okay. So V a vector space and X some guy in V, then the scaling of X is the 0 vector. Okay. So these are things that you're going to be like, what? We have to conclude that? That's not obvious? Well, we have to get it from the vector space axioms. Okay, and you're not going to like it. I don't like it. Okay, that's the first one. The second one is that if x plus y is the 0 vector, then y has to be the additive inverse of x. Okay. So in other words, the additive inverse is unique. Right? That you know that there's somebody you can add. You know that there's somebody you can add and get the 0 vector. Okay. It turns out that there's only one guy that works, and that's the additive identity. So if you add somebody to it and you get the 0 vector, that guy must have been the additive identity. Additive inverse, excuse me. Third, seemingly obvious property, that -1 times x is actually negative x. The additive inverse actually is the -1, the scaling by of the vector by -1. So I'll show you the proofs of these, and then you can forget them, okay? Because it's like the most tedious and sort of disgusting thing you've ever seen. But okay, it's not disgusting. I shouldn't say it's disgusting, but it's extremely tedious and it's sort of like makes your skin crawl a little bit. Okay, so proof of number 1, we want to show that 0 times x is the 0 vector. Okay, so here we go. Say, well, x is 1 times x by axiom, whatever it was, by axiom S4. By axiom S4, which is the same thing as 1 plus 0 times x, just by numbers. 1 plus, 1 and 1 plus 0 are the same thing, of course. So that is x plus 0x by the distributive property, which was x2. Okay. Well then, the 0 vector is negative x plus x by whatever axiom that was, A4. Right, because if you add something to its additive inverse, you get the 0 vector. Right, which we just saw that x is equal to this, so we're going to rewrite that. This is x plus 0x, right, by the above. Okay. And then you say, okay, and this is equal to negative x plus 0x, right, by associativity, right? Because addition is associative, vector addition is assumed associative, and so you get 0 vector plus 0x, right, by, again, A4, and that's 0x. That's 0x because this is the additive identity, A3. Okay, so what do you get? That 0 times x is the 0 vector. Dun dun dun. Okay. Okay. So, right, and it's sort of like, okay, my God, don't we know that? And the point is that actually you don't know that. You don't know that. You're in the world of abstract vector spaces, but it turns out that it's the reason 0 times anything is the 0 vector is because of the axioms that you assume. Okay, so yeah, okay. So let me quickly go through the second one. It's just I'm not going to have time or interest in doing the third one. So I just do it here. So number 2, you want to show that x plus y being the 0 vector forces y to be the additive inverse of x. See? Okay, you say, well, negative x is negative x plus the 0 vector, because the 0 vector has that property. So that's negative x plus the 0 vector, which we said was x plus 1 by hypothesis. But then you use associativity, right? Negative x plus y by associativity. So it's going to be 0 plus y, which is y. And so what you get is that if x plus y is the 0 vector, then y must be negative x. Okay, and then the third one, goes along the same sort of lines. It's not exciting. These are probably the simplest sort of proofs that you can do. I heard from an ex-student that she once went to a math camp, and this is how they started them off, like with basic axioms and proving extremely seemingly obvious statements, right? But it's good practice to say, okay, we only know these facts. What can we prove from them, or how do we prove things with them? Okay. And so that's why I've shown them to you. But I don't really care about this sort of thing in general. Okay, that's it for today.